So the first of the ideal gas laws is easy to understand if you grab a syringe, and if you just apply just a little bit of pressure, you'll get the volume. You can almost feel like you can just squish it to nothing. But then you soon discover that it just stays there, and no matter how much pressure you apply, you massively increase the pressure and the volume doesn't decrease at all. So you can see it's not a straight line, and so it is this curve here. And so that means pressure is indirectly related to volume. So if we increase the pressure, we decrease the volume, or decrease the volume, we increase the pressure. So it's indirectly related. So if we reverse that around, times both sides by V, that gives us a constant. So P times V equals a constant. And so any situation of P1, V1 will equal this constant P2, V2. And so that's our first gas law. So we can have a pressure and volume, and then we can predict, well, if we change the pressure, what's the new volume? Or if we want to change the volume, what pressure do we need? So we can solve pressure volume problems with that. And that's assuming, of course, temperature is constant, number of moles is constant. So whenever we do these gas laws, we're going to play around with these three, assuming that the number of moles is always constant and one of the other three are constant. But we're not going to worry about that at all, because we're going to do PV equals nRT and combine the whole lot in a second, but that'll be in the last video. Okay, this is also a trick. The physicists are good at turning these curves into straight lines. If you don't believe that that's the case, have a go at grabbing all the values and getting one and dividing it by that, and then replotting it. It'll come out as a straight line. So just be careful that you check your axes if you think, well, that can't be the pressure volume graph because it's straight. Just have a little check down here that they haven't tried to trick you. All right, so the next one is volume versus temperature. So you'll find if you increase temperature, you increase volume, and ideally it is a straight line. And so that's volume is directly related to temperature. Increase one, you increase the other. And so you divide both sides by T, that gives you a constant. So volume 1 and temp 1 in any situation will be the same number as the volume 2, temp 2 in any situation. So again, you can solve problems for one of these as an unknown. Now, interesting, the way we get our temperature scale is by extrapolating these graphs. And so if you get the volume graph, for example, the volume temperature graph, there should be a point, if it was an ideal gas, where it will go to zero volume. And if it goes to zero volume, that is the point at which there is truly no kinetic energy left. And that is true, 0 Kelvin. We've worked that out to minus 273.15 degrees Celsius. That is zero temperature, 0 Kelvin, 0 kinetic energy. Although I don't think they've ever quite got there. They get really, really close. And the last one we're doing is pressure versus temperature. So again, you increase temperature, you increase the pressure with a fixed volume. So remember, one of the three is always fixed and number of moles is always fixed. So again, you divide, and then you have this pressure volume relationship in two different situations.